Good morning, everyone. Today, I'm going to talk about Maxoid, transparently confining mobile applications with custom views of state. It's a joint work with my advisor, Emmett Witchel from UT Austin. The focus of this work is a type of security problems on mobile platforms, which is when different apps interact with each other, the secrecy or integrity of the user's data is often compromised. And the cause of such problems is the insufficient support in existing platforms, and they can't be fixed without modifying the security model of current platforms. The security model for mobile platform is app-centric. For a typical mobile device, there's just one user, one platform, but many apps. These apps are from many different developers. The user may not trust them, and they may not trust each other. In this sense, these apps are the principles in terms of security on the platform. And it's a vital responsibility for the platform to minimize the privilege assigned to each app, as well as to protect apps from each other. Here's a high-level abstract view of the data model in the mobile platform. Each app has some private data or private state. They also share some public state, like a photo gallery and a list of contacts. Note that here, public and private are in terms of apps, not users, because there's just one user on the platform. And this simple model actually applies to many existing platforms, including Android, iOS, Windows Phone, and Firefox OS. Let's take a closer look at Android. In Android, each app store runs in its own process with a dedicated Unix UID, and such a process is a sandbox created for this app. The app stores its private data in private files, and the kernel will prevent other apps from accessing them. There are also higher-level APIs, such as the database and key value store, but they are implemented as user-level libraries. For instance, a banking app stores the user's account information in its private state, and an email app stores the user's emails and attachments in its private state. Android also provides some public data shared by apps. They include the raw files in external storage, like the SD card, as well as some structured data defined in system content providers. Content providers are mechanisms in Android to define database-like APIs in order to share structured data with apps. Contacts, media, and download metadata, and user dictionary are all managed by system content providers. However, as we'll show, this clear separation of public and private data is insufficient to support many important use cases securely. The problem is sometimes an app needs to share its private data with another app. For example, you may receive an email which contains a PDF attachment, and this attachment is sensitive and you don't want to share it with arbitrary other apps. However, the email app has no ability to open this PDF file, so you have to leverage another app, Adobe Reader, to open it. In this scenario, we say the email is the initiator, which means the app that holds the private data to share. And Adobe Reader is a delegate, which means the app that processes the private data received from its initiator. In this use case, the initiator email has to disclose this file to the delegate Adobe Reader in order to make it accessible. However, the problem arises at this point. The way Adobe Reader works is not aware that this input is private, so it doesn't take extra care to keep this file private. And even if it does know this is a private file, it might not even know what the right thing to do is, because it's a private file from a different app. And in reality, we observed that every time you open a PDF attachment from email, Adobe Reader will always make a copy of this file to the public SD card. In Android, initiator apps don't have a way to protect the data sufficiently when they want to share them. The email app has no confinement on the document viewers for the attachments. The Dropbox app simply stores all users' files on the public SD card to allow other apps to open them. Again, there's no confinement on the document viewers it invokes. And many browser apps provide incognito mode, which means when the user terminates the browsing session, all browsing history will be erased from the device. However, currently, even with incognito mode, downloaded files are public and they are accessible by other apps. And these other apps may make copies of these files, and the browser has no way to erase such copies. So the contribution of our work, Maxoid, is to secure such use cases while maintaining high usability. First, it uses coarse-grained information flow control to confine the delegates such that they can't leak data. And second, it is designed to support legacy apps. And the key technique is to use multiple versions of data organized in custom views of state for different app instances. And this technique is very important for high usability because, as we'll show later, a naive information flow control will cause usability issues in different ways. We've done some study on over 70 popular apps that can be used as delegates. They include popular document viewers, scanners, cameras, and media players. We found that if we use them as delegates to process some input from the initiator, they will leak data about this input into the public state in different ways, including copies of files, thumbnails of photos, and metadata in different formats. They may also send the data to the network. So an obvious way to solve this problem is to use a very simple information flow control mechanism where it confines the delegates such that they are disallowed to leak data to the public state or the network. The good thing about this approach is that mobile apps typically tolerate temporary network disruption. However, the problem is they don't tolerate disruptions in the public state. So if we naively block data flows into the public state, these legacy apps will break because they will get unexpected permission errors. And even if they handle such permission errors correctly, what they do is usually just throw an error message to the user and stop working. To avoid this problem, we might try a different approach where the system performs taint tracking on the input data, and delegates are still allowed to write tainted data to the public state. Here, we use the orange dots to represent tainted data. And the system disallows any app to write tainted data to the network. However, the problem about this approach is that the public state is shared by all apps, and other apps like Facebook and Dropbox may also read in the tainted data, such that, and at that point, they are also confined and lose network connection. So the problem of this approach is that it is too permissive about the public state, so that uncontrolled taint propagation will cripple the functionality of many unrelated apps on the device. In summary, there's a dilemma in the naive information flow control. If we allow the delegates to write tainted data to the public state, there will be the problem of uncontrolled taint propagation. But if we disallow, legacy apps will break. So to address this dilemma, we present Maxoid, which is a new way to do information flow control for a mobile platform. It still allows delegates to write tainted data to a public state in order to avoid disruption. But it also controls taint propagation in a transparent way, such that tainted data will not affect unrelated apps. So the key technique is that when necessary, Maxoid creates multiple versions of data and isolates tainted versions from untainted versions. Then it presents different views of state for different app instances to make the confinement transparent. In Maxoid, an app can run in one of two modes. The first mode is the normal mode, where we say it runs on behalf of itself. In this mode, it runs in exactly the same way as it would run in Android. And we say it is an initiator in this mode. In the second mode, we say it runs on behalf of another app, and it is called a delegate of the other app. And the other app is the initiator for this delegate. For typical use cases, the delegate is expected to process some private input received from its initiator. For example, Adobe Reader can run on behalf of email as a delegate. As shown on this slide, to represent a delegate, we stack its icon on top of the initiator's icon. Maxoid uses very coarse-grained taint tracking, where all output of the delegate is considered tainted by the private input from the initiator. So it's a very conservative approach, thus it's very easy to provide strong security guarantees. On the other side, generally speaking, coarse-grained taint tracking suffers from usability problems caused by false positives, which means it usually recognizes safe data flows as unsafe ones. However, with the technique of custom views of state, Maxoid makes it usable. This is an overview of confinement for Delegate. First, Maxoid creates copy and write views for the public and private state for Delegate. These views involve both the files and data in system content providers. The copy and write views help achieve both secrecy and integrity because they confine potential data leaks and prevent overwriting the original version. Second, the delegate is prevented from accessing the network. And finally, the delegate can only do IPC with other delegates on behalf of the same initiator, so it can never leak data by sending data to other unconfined apps. So before we go into the detail of the Maxoid views, let's look at how it can secure the use cases we mentioned in the beginning of this talk. First, for email, with Maxoid, it can confine the document viewers as delegates for the attachments. The nice thing about this scenario is that we only need to add a few lines in the static configuration file of this app, and we didn't modify a single line of source code. For Dropbox, Maxoid allows it to store the user's files privately and invoke delegates to open them. Again, we only modified the configuration file of Dropbox. And for the browser's incognito mode, we only added one line of source code such that the private downloads from an incognito tab are private to the browser app, and only delegates of the browser can open them. In this way, we have extended the incognito mode from the browser to the entire device because the traces left by the delegates can be easily erased when the user terminates the browser. Okay, now let's go to the details of the Maxoid views. First, the views for initiators are identical to Android's data model, where an initiator can directly access its private state and the public state. In our scenario, the email has the PDF attachment in its private state, and Adobe Reader maintains a list of recent files in its private state. But when Adobe Reader begins to run on behalf of email as a delegate, the system creates copy and write views for its private and public state. Next, the private state of the initiator email is included as part of the copy and write view for the delegates. In this way, Adobe Reader is granted access to the PDF attachment. Then, when opening this PDF attachment, Adobe Reader will add a new entry to the recent file list for this attachment. However, this update is confined in the copy and write view. Then it may also write to the public state. Again, these writes are confined in the copy and write view. The delta data in the copy and write view for the public state is invisible to other unrelated apps, so Adobe Reader and the delegate can never leak data by writing to the public state. On the other hand, the delta data is visible to the initiator email, but it doesn't directly overwrite the original version. So consider a natural use case where the user actually wants to save some desired changes in the delta data, such as some notes taken on the PDF file. But everything else in the delta data is considered side effects that the user doesn't want to keep. To support this use case, the initiator can simply save this edited PDF file. And after that, it can erase the entire delta data. Okay, now let's move to the private state of the delegate. The delegate has updated the recent file list in the copy and write view to include the attachment. However, this update is not persistent. It will be discarded by Maxoid eventually. So if next time Adobe Reader restarts normally as an initiator, it will only access the original recent file list, which doesn't contain any tainted data, so it will not be confined. And if it restarts again on behalf of email as a delegate, the copy and write view is recreated, which doesn't contain the attachment file. So you may see that there is a potential usability issue, which is whenever Adobe Reader runs as a delegate, it can't save a persistent update to the recent file list. So to address this problem, we introduce a new but optional API, which is the persistent private state for delegates. Adobe Reader can use this API to maintain a list of recent files received from email, and it is only accessible when it runs on behalf of email. So when opening the attachment file, it will add entry to this email attachment list. And if it restarts in normal mode as an initiator, it will no longer have access to that recent attachment list. And then if it restarts again on behalf of email, it regains access to the attachment list. This API is optional, and it only exists for better usability. In summary, with the custom views of state, Maxoid achieves such usability properties. First, its confinement is transparent for delegates, because the delegates can still read and write everything in its view of state. Second, the tainted data will not affect unrelated apps. And finally, the initiator can get a result back from the delegate, even if the delegate cannot directly overwrite the original data. And here are some implementation details of Maxoid. The Maxoid views contain both the file system and the data in the system content providers. For the file system, we leverage the mount namespace mechanism in Linux and use a unit file system, AUFS, to mount different branches of the file system to different app instances. In this way, we implemented per-file copy and write for delegates. System content providers typically use SQLite as their backend for storage. We wrote a proxy layer on top of SQLite to achieve per-row copy and write. And we still need some provider-specific modifications to make them use the copy and write layer. Another detail is that the user may consider some attachments are sensitive, but others are not. To support this distinction, we allow the initiator to invoke other apps in different modes. It can invoke a document viewer in the confined mode as a delegate, or it can invoke the document viewer in the normal mode, which is initiator. There are two ways to specify this distinction. The first is to statically specify with the configuration file of this app, and the second way is to dynamically specify with a new API. It allows finer control on the types of different invocations, but it requires code change. And finally, let's briefly talk about the performance of Maxoid. Maxoid has no overhead for CPU-bound workloads. For file system and system content providers, it has negligible overhead for initiators. For the delegates, the worst-case scenario is when a delegate makes the first write operation to a large existing file. And the overhead depends on the size of this file, which can be arbitrarily large. This is because we won't have a per-file copy and write mechanism, and this limitation can be alleviated if we had a per-block copy and write. For other micro benchmarks, we observed between 0 and 31% of overhead. For macro benchmarks, Maxoid adds negligible user-perceived latencies for typical usage of real-world apps, including Adobe Reader, Camera MX, and Cam Scanner. To conclude, information flow control can prevent data leakage in mobile platforms. Maxoid uses very coarse-grained conservative information flow control to achieve strong security guarantees. And it also uses per-app instant custom views of state to make the confinement transparent. That's all about my talk, and thank you.
Questions? So for one question, is there some way that someone can defeat your approach?
There could be side channels which we don't consider, and in terms of the model, the delegate is completely confined, and it can never leak data.
Okay. Other questions?
Hi, Jeremy Andrus, Apple. So a lot of times, a lot of processes in mobile devices can be long-lived, and you talk about confining delegates and things. Do you require, like say if an instance of Adobe Reader was already running, do you require killing that instance and restarting a new one? Or
currently we start a new one, like if it currently runs as in a normal mode, and if we want to confine it, we simply start a new one.
Okay, so you would you kill the old instance?
Yes.
And then, okay, thanks.
Okay. Thank you. It reminds me of a simple question because sometimes your device makes screenshots from the application so that when you browse the windows of opened application, you can sometimes figure out what the application was currently displaying when it was closed. So do you prevent this kind of stuff? Because if you open something which is secret in terms of information flow, then it can still be displayed by a screenshot. So do you address this problem?
Sorry, I didn't get the last sentence.
Oh, yeah, sorry. I was saying that the application basically takes a screenshot so that when you restore the application...
Screenshots?
Yes.
I think the screenshots...
From the operating system, I mean, you know, when you restore the application, sometimes you just have the picture of the last state. Yeah.
Yeah, we haven't considered that yet, but I think that's a good point.
Any more questions?
Hi, Cheng Tan from NYU. So I have a question about when the delegate is, invoked by another application, it has its own UID, or it shares the same UID with its,
With its normal mode, you mean? Yeah, it still has the same UID, but its view of the file system is changed. So it's confined by the mount namespace, so it can't overwrite the original files.
In this case, the delegate is still running its own UID, but cannot see anything inside the file system. It will change.
You can still see everything, but if it's a write, this write will, like the copy and write will happen to confine such updates, so that it can't leak data by writing out.
Okay, thank you.
Okay, let's think to speak.